So we're now set to cover our final pattern in our discussions of patterns that arise in the context of Android and Java concurrency. Be aware, of course, that there's lots of other patterns above and beyond the ones that we've covered. There's plenty of other gang of four patterns that are used throughout Android and Java concurrency frameworks, things like template method and factory method and strategy and so on. But we've been focusing primarily on patterns from the POSA 2 book. So we covered the monitor object pattern, we covered the active object pattern, we covered the thread-specific storage pattern, the command processor pattern, and now we're going to wrap up our coverage with focusing on the half-sync, half-async pattern. And this is a pattern that originally appeared in the POSA 2 book, and then you can also find links to preprints of the pattern that are on my website as well. So as is our tradition, let's begin with a discussion of the context in which we're going to be looking at this pattern. So concurrent systems, say like Android and Android apps, often have to perform both asynchronous and synchronous processing services. And it's often the case that these synchronous and asynchronous services have to communicate with each other in order to carry out their tasks. And I'll show you some examples of this, the most important of which will be the threaded downloads app, which you can get from the link at the bottom of the slide below. And what this app does is it basically is an Android app with a bunch of different buttons. You can push different buttons and it'll go ahead and download an image from a remote server, and then it'll display it in the user interface of Android. So what are the problems here? Well, sometimes it's the case that you want to have the simplicity of synchronous processing, because that is easy. You can block. Synchronous, another synonym for that is blocking. So you can do blocking IO operations in a synchronous way. And you don't want to have to make the whole app be asynchronous. Asynchrony is cool. There are technologies that enable it, like, say, RxJava or Project Reactor or Java Completable Futures. But to be honest with you, doing an entirely asynchronous app is a bit more complicated. And we'll cover some of those complexities in the course I take next year, the course I teach in the fall of 2021. So I hope you can take that course. But if you can't take that course, just be aware that it takes extra knowledge of patterns of asynchronous programming to do an entirely asynchronous app. So we'd like to be able to do some things synchronously. So for example, downloading the image itself. If you take a look here, you can see that there's a method called download image. You give it a URL, and it goes ahead and downloads a bitmap. And what it does there is it uses a feature that's built into the Java class libraries, which is the URL class. And you say new URL, passing in the URL for the image you want to download, .get content, and that will go ahead and block. And it'll download the image, convert it into an input stream, and then we basically decode that input stream and turn it into a bitmap using a factory method on the bitmap factory class called decodestream. So every thread that's going to be doing this needs to be able to block independently. And the reason for that, of course, is if you end up with a large file or you end up with encountering flow control during the download, you don't want to degrade the quality of service from other threads that are doing the same thing. Now, the way this all has to work under the hood, of course, is we want to be able to have the synchronous and asynchronous processing communicate without unduly complicating the programming model. We don't want to make this really hard to integrate these two different styles of processing. And of course, we also want to try to ensure performance remains good, because there's no point in using multi-threading if your performance goes out the window. So the way we're going to do this is we're going to end up with a user interface thread, which you may recall from previous discussions has to be non-blocking or asynchronous. And then we're going to have some background threads that run and do the actual downloading, and they're going to be synchronous. So we're going to have this sort of half-sync, half-async model. We also, of course, don't want to spawn an unbounded number of background threads, so we're probably going to have a pool of those. So the solution we're going to apply here is to apply synchronous and asynchronous processing in a clever way using the half-sync, half-async pattern. And the way this pattern works is it structures the services, the things your app is doing, into two layers, the synchronous services and the asynchronous services. In this case, the synchronous services are those blocking threads that are downloading the images that you want to display from remote web servers. And we could put those into a pool so we can bound the number of threads or keep it fairly close to bounded. If we might grow it a little bit, but we probably want to bound it ultimately, so that we can map those threads to the different cores efficiently, but not get carried away and have a thread for every client or every URL that's being downloaded. And then for the asynchronous part, we're just going to have a single thread. And in this particular case, since it's Android, of course, we're going to use the user interface thread to do that portion. And then to mediate between the two layers, we're going to use a blocking queue, which of course will be a good old Java blocking queue, or it could be some other kind of blocking queue. It doesn't really matter. It could be a blocking queue that's baked into Android, like the message queue mechanism and so on. And we're going to end up using something called the AsyncTask framework to make all of this stuff interact properly. And the AsyncTask framework, as we'll see, is a very interesting class framework that's provided in earlier versions of Android in order to be able to decouple the user interface thread, which is single-threaded and asynchronous, from background threads, which are blocking and synchronous. But before we get into the details of how all this works, let's take a step back and talk about the intent and the applicability of this pattern as it's disclosed in the POSA 2 book and that paper I mentioned. So the intent of this pattern is to decouple the asynchronous or async services from the synchronous or sync services in a concurrent system, like an app, by introducing two intercommunicating layers, one for the async and one for the sync. And we're going to do this in order to simplify programming without unduly degrading or reducing performance. Here's the link to the paper. If you don't have the POSA 2 book, you can take a look at this paper, which has kind of a preprint of the material that's covered in the POSA 2 book. So when should you apply this pattern? You should apply this pattern when you want to make performance efficient and scalable, but also trying to make your code as easy to program as possible. And that means trying to do blocking operations in the synchronous layer, and then non-blocking operations in the asynchronous layer, and then queuing up communication between the two layers using a message queue that sits in the queuing layer, which is the layer that mediates between the synchronous service layer and the asynchronous service layer. Another reason for using this is when there are constraints on certain types of operations in certain contexts. So for example, you might have some short-term operations or short duration operations that could run entirely in the async layer because they don't block, they don't run for long. You may have longer duration operations. They need to probably run in the async, in the synchronous layer in separate threads so that they can do their thing without having to worry about blocking other operations. There's non-blocking versus blocking. So there's a whole bunch of different sort of trade-offs and considerations to decide where the services are actually going to run. This particular pattern, as we'll see when we get into some of the known uses, is very widely applied in a range of different computing systems, going all the way from operating systems and the operating system kernels, which is the kind of thing you'd cover in our OS course at Vanderbilt or OS courses, as well as modern user interface frameworks, which is really how it gets applied in the context of Android. So what are the roles and responsibilities and the structure and participants in this pattern? Well, you can see there's a bunch of them. We'll start out with the asynchronous service layer first. That's the part that is not going to block. It's going to be short duration operations. And in our particular example, that's from the Android environment, that would be the user interface thread or the UI thread. And just recall, you can't do long running operations without incurring the wrath of the dreaded application not responding dialog popping up and saying, do you really want to continue or should you terminate this application that's blocking? Between the async layer and the sync layer is the queuing layer, and that's where you put requests that are going to be taking longer to process than can be handled in the non-blocking async layer. And in the context of Android, that would be some kind of blocking queue. And then at the other end of the spectrum, we have the so-called synchronous service layer, and that's what's going to contain these synchronous services that will run in their own threads of control and therefore can block without degrading the quality of service of other things that are also blocking in their own threads. So these would be the background threads in the context of our downloading app. So now you have a basic idea of the structure of this pattern. Let's talk a little bit about its dynamics. So here's basically how it works. We're going to have the various roles we just talked about: the external event source, the async service, the queue, and the sync service or sync services. And so an event will occur. For example, the user will provide a URL that you want, and that will be handled by the graphical user interface, and it takes that event, brings it into the system, and then that event will be handed off to the async service layer, which will do something with it. In our particular case, that's going to be used to start up an async task, and that the starting of the async task is not going to block. It's going to be done asynchronously. Then you can queue requests without blocking the caller in order to pass information from one part of the requesting chain to the other. And then any long-running application processing will run in the synchronous service portion, which in our case is going to be within a pool of threads that's managed by the underlying async task framework that Android provides. So just to keep in mind, services will run concurrently because they've got threads from a pool of threads, and they're concurrent with respect to each other because different threads can be blocking, downloading different content from different servers or the same server. And of course, these services also run concurrently with respect to the asynchronous portions, which are getting work in from the user interface. So we'll talk more about the implementation of this pattern when we get to that part in the next video. But right now, I want to talk about some of the pros and cons of this particular pattern. So perhaps the best benefit is simplification of programming by trying to do a lot of the long-running work in separate threads so they can block, which is easier to program in many ways, without throwing performance totally out the window. So we're able to do the long-running computations in threads, but if there were short-running computations, they could be handled directly in the async part, the user interface thread part, for example. And you can see here just kind of the different constituents that are part of the async task framework. We'll look at that in more detail in the next part of the lesson. There's also a nice separation of concerns, which is a benefit. So you can have synchronization policies in the different layers decoupled from each other. So they don't have to use the same concurrency strategies. They don't have to use the same synchronizers. They can do whatever's right for their layer in the most optimized way. Another nice benefit of this is we can centralize communication between the layers because all their interactions can be mediated by this queuing layer, which usually just has one queue, as we do here, but it could in fact have multiple queues. As always, not everything is unicorns and rainbows, so there's some downsides. When you move events or messages from one layer to the other through the queuing layer, from say the async layer to the sync layer through the queuing layer, that can incur what's called a boundary crossing penalty because you're going from one thread in one context, say the user interface thread in the user interface context, to some background thread in that background thread's context. And that involves context switching. There's some synchronization overhead involved to protect the data structures that are used for the queues. There's data copying overhead at the cache level. There's the fact you have to allocate memory dynamically to pass them between the layers. So there is some overhead. The basic rule here is if you're doing a long-running computation, the fact that there's some synchronization and context switching overhead is kind of in the noise. But if you're doing something that takes a very short amount of time, then the overhead will dominate. If you're doing something that takes a long time to run, then the overhead won't dominate. So you'll be fine. You can take a look at this link below, which is actually something based on my PhD dissertation from a really long time ago. Gosh, it's hard to believe how long ago that was. That was, I think, over 25 years ago. And it kind of talks about the way in which all this stuff works. Another consequence of this is that if you need to have these long-running operations, they're going to be using synchronous processing in separate threads. And if you have really good support for asynchronous processing, which is sometimes the case in modern operating systems like Windows, for example, those application services and so on won't be able to benefit from asynchronous I/O because we've got a synchronous processing portion at the top of the pattern. If that's the case, then if you need to be able to leverage the asynchronous I/O, you probably want to use an entirely different pattern altogether, which would be the Proactor pattern, which unfortunately we won't have time to cover in this course, but it's also a very interesting pattern that's worth being aware of. And of course, as is always the case, whenever you've got systems that have concurrency and asynchrony and so on, and threads, you're going to have extra complexity for debugging and testing because there's just more stuff running around. This is not really a defect of the pattern per se. It's just a consequence of the fact that concurrent processing introduces a lot of non-determinism, and you just got to kind of suck it up and get used to dealing with it. So where is this pattern actually applied? Well, there's lots of interesting cases where it's applied. One really cool case where it's applied is in the network subsystem of operating system kernels like Unix or Linux. So if you take a look at the link at the bottom of the slide, which is a paper we wrote prior to putting this into the POSA 2 book, you'll see a nice description that maps the patterns, roles, and participants and structure and dynamics onto the implementation of the BSD operating system networking subsystem. And it's really cool because it kind of shows how the mechanisms that are available in the kernel for handling requests from network interfaces, like a network device that's connected to your laptop or to your desktop or to your server or to your phone or whatever, uses this pattern to structure the way in which the operating system kernel receives the information, processes it asynchronously, and then plops it up into a socket queue where it's eventually processed by processes or threads that can block running at the user level. So a really good example of how patterns are used in a low-level way. This pattern is also widely used in object request brokers, or ORBs, which were a popular technology in the 90s for being able to do distributed object computing. And if you take a look at the link at the bottom of this page, you'll see a description of how we implemented the half-sync, half-async pattern in the context of our Corba implementation called the ACE-ORB, or DAO. And in that case, we had an asynchronous part at the bottom, which used yet another pattern implementation called a reactor. And then we had a queuing layer, and we had a bunch of active objects that were running up there processing the request. So it was kind of reactor plus active object equals half-sync, half-async implementation. So another cool example of where this pattern has been applied. And of course, in the context of Android, and Java for that matter, which is our focus for a concurrency perspective here, the Android AsyncTask framework is where this pattern is applied in Android. And we'll talk a bit more about async tasks, but basically they're a way of being able to do asynchronous computation where the long-running operations, the long-duration operations run in a pool of background threads that are managed by a Java executor, like the executor, the thread pool executor, or a fork join pool executor or whatnot. And the user interface thread is then responsible for initiating or executing the async task, and it doesn't block. So we'll see how that works shortly. So to summarize this part of the discussion, the half-sync, half-async pattern is used to separate concerns between these three layers, the async part and the sync part through a queuing layer, which helps to make software easier to debug and evolve and understand when it's used in concurrent context. The async and sync parts are nicely decoupled, so you don't have to pay the liabilities of this stuff. The nice performance boost you get from asynchronous programming doesn't complicate the programming, because asynchronous programming is more complicated. So you kind of get, hopefully, the best of both worlds. And so you can pick and choose which things you use where. And having a queuing layer allows you to be able to decouple the relationships and the different mechanisms that are used by the synchronous and asynchronous services. Another reason why the queuing layer is helpful is it allows you to do things like reprioritize the order in which incoming events or incoming messages are processed by the synchronous services, because you can rearrange them and reprioritize them in the queuing layer. So that's the end of the overview of the half-sync, half-async pattern, looking primarily at the kinds of things you'd read about in the POSA 2 book, with respect to intent and applicability and structure dynamics, consequences, and known uses. And then in the next part of this lesson, we'll turn our attention to how this is actually implemented in Android.